Okay. Hi. So today's meetup. This is supposed to be a developer meetup, but this talk is going to be a little bit more on the theoretical side. So it's the title is unfairly linear signatures. That's just a joke, but it's talking about Schnorr signatures, right? So there's something that could, in the near future, have a really big practical significance in Bitcoin. I'm not going to explain all the practical significance, but to give you an outline, the outline is something like some theoretical stuff. So I'll explain what all these terms mean and how they fit in shortly. Some theoretical basis for what I'm trying to get at is, what is a Schnorr signature? Where does it come from? Why is it done the way it's done? And is it secure? And that's what these kind of early theoretical parts are about. And then after that, we'll actually start to look at uses of Schnorr signatures, specifically in Bitcoin or related to things in Bitcoin, and a little bit about security. And also expanding this onto things called CoinSwaps and multi-sig with ECDSA. This is actually kind of a sidebar, but let's just say all these later parts of the talk are about ways we can use Schnorr signatures and, to a lesser extent, ECDSA to do interesting things. That's a kind of really vague coverage. Now, this first kind of half, which is the more theoretical, I'm going to try and get you to sort of let me know how you feel about it. You know, do you find it interesting? Is it all just gobbledygook, or do you find it's really cool, interesting, and you want to learn more about it, in which case you might need to ask somebody who knows more about it than me, because my level of knowledge of this is okay-ish, sort of high level, but I'm not going to give you like a full university lecture about all the theoretical, all the theorems and all that stuff. It's more slightly higher level. But the reason I want to look at it is because I think sometimes these things that we use, if we're either developing Bitcoin or we're just kind of in that area, it all seems a bit magical, like why is the formula for ECDSA the way it is? What is an elliptic curve? This stuff is all a bit magical. So to whatever extent I can, I want to give you some intuition and some kind of feeling for what this object is. And I think the Schnorr signature is particularly suitable for that, because it's actually much simpler than a lot of other things. Like if we started having a talk about the elliptic curve addition formula and writing out all the algebra of it, we'd have to go back into some incredible long spiel about mathematics. It's very complicated. And we don't need to do that. Similarly, ECDSA is a little bit more complicated than Schnorr. So it's actually, even though Schnorr is coming after ECDSA and Bitcoin, Schnorr is actually simpler to understand. So that's what we're aiming to do here. And then, as I say, second half, a bit more practical, but still quite theoretical about the applications. So to go anywhere with this, we first have to understand the idea of a commitment scheme. And to introduce the topic of a commitment, I want to suggest you think about a game, which you may have thought about before. And I called it the telephone game. That's kind of weird, isn't it? The telephone game, like Chinese whispers, when you... I don't know why I called it my idea is this, right? Everyone knows about tossing coins, right? So your heads heads or tails, and you choose, right? That's a very well-known thing. But if you wanted to do that over a communications channel, so suppose I and Chris were going to bet on the toss of a coin, Chris is going to call it heads or tails, I'm going to actually toss the coin. Now the problem is, if we're over a telephone, then we can't see what each other are doing, so it's not safe. So if he calls heads, I can just say, oh, I just tossed it and it was tails. And he doesn't know if I'm lying. Well, of course I probably am lying if there's any incentive. And vice versa, it's not safe for me if I toss the coin first and say it's heads and he says, oh yeah, I did choose heads. It's not safe. Right, so how do you avoid that problem over a communication channel? And the marvelous thing is, it turns out you can avoid that problem specifically if you have something that we might call a one-way function. So if you can get something where, given the output, you can't retroactively figure out the input, you can achieve this goal. So I'm not going to sort of set it as a puzzle. You either know the answer or you don't. the most natural and obvious answer involving things that we might be familiar. I mean, everyone here is familiar with hash functions, right? Yeah, okay. So using a hash, I hope you can see that this is the right way to solve that problem. Maybe there's some tweaks you'd need to make it a completely perfect protocol, but I don't care. So the general idea is, if Chris, well, let's just say Alice and Bob now, if Alice hashes the choice that he makes and then gives Bob the hash, then Bob can safely reveal the result of tossing the coin. Now there's some details to that. If Alice just hashes, let's say, the string tails, so I get some 32-byte random string, sends that over to Bob on the telephone wire or the communications channel, that would not really work. Do you know why that wouldn't work?
Yes, Bob can pre-compute the hash of tails and heads.
And hash of heads, right? So you can simply compare the result and see. And so what is the failure in that? The protocol without that part is a failed protocol because it doesn't have a property called hiding. So I actually really do wish I had a coin now. I think it's a very physical and visceral thing. No, it's okay. It's a very physical and visceral thing, isn't it? But we're all used to that concept of that, right? And what that does physically is first of all, it hides the result. So the problem with just doing hash of tails, it doesn't hide the result. Whereas if we include a long random string, we are actually getting the hiding effect of whatever the result was. But the other effect we have is we need it to be the case that having done this, I can't sort of do that, right? So that's what we call binding. And that's where the hash function's property comes in, because having computed, I think I wrote this as the next thing, yeah. Having computed the hash of tails plus a long random string, and getting a certain 32-byte or however many bytes random as a result, Alice can't then lie after Bob has revealed his result is actually heads. She can't then make up a random string that gives the same hash with heads. She can't, if she puts heads here, she can't find a random that gives the same hash output. So that's second pre-image resistance, I believe is the technical term. But you know, hash functions have these certain very specific properties, or at least we want them to have these specific properties to behave well. So that's the idea of a commitment. So think of it. So what we could say there is that solves that problem. It gives away Alice can't cheat, and Bob also can't cheat because he can't know what Alice chose. Everything making sense so far? Yeah. I mean, I can tell from the room that you either already know all this, or it's very obvious to you, so that's good. That's good news. So toy example that we just gave illustrated two key properties, hiding and binding, right? A commitment scheme is generally considered of, I may be remembering this somewhat wrong, but I think there's basically three aspects. There's like a setup, and then there's a commitment and an opening. Yeah? So commitment and opening. Commitment is when Alice produces her hash result. And opening is when Alice says to Bob, actually, these are the data, this is the data I use to generate that hash. So that's commitment schemes. It's very, very important for what we're going to discuss next, which is the sort of zero knowledge proof of knowledge and the Schnorr stuff. I'm trying to cut down on words. We can do the same thing as that, but using elliptic curve points. Is everyone familiar with, because this is going to crop up increasingly frequently as I talk, is everyone familiar with the idea of adding two elliptic curve points together?
Like, very broadly on a picture, but if you can get less more details, that will help a lot. Right,
so I don't mean, it's ambiguous what I mean. I'm going to go over here. It's ambiguous what I mean. I don't mean drawing out, curves and all that stuff, no. All I mean is, so if I have let's talk about public and private keys because it's something we're hopefully all familiar with, yeah? So public, keep this in mind as we go through the talk, is that model in our head of a generator point. This is actually a point on the curve, but it's a specific, publicly known generator point, multiplied by a scalar number, giving another elliptic curve point. Yeah. So that process, or mean, this is kind of implicit here, that there's a multiplication. It's an elliptic curve scalar multiplication. It means g plus x times, right? And that's called scalar mult, or scalar multiplication. And of course, it's not the fundamental operation, which is mult. The fundamental operation is adding two points together, which can, of course, include. So it's a group with an addition operation defined for it, yeah. And of course, you can add the same point to itself, and then we call that 2a. So this addition is equivalent to the scalar multiplication of the number 2 by a. All right, just because it will come up again and again. Right, so we can do commitments using elliptic curve points instead of using cryptographic hash functions. But there's a whole section of 2 or 3 slides about this, and I realised that it's kind of not related to the rest of the material, so I'll skip it, but if at the end you want to ask me about it, you can. So I mentioned in particular on this slide the Pedersen commitment, which is where you, see here you'll see this notation again, right? So we take lowercase letters meaning scalar numbers, actually numbers modulo the order of the group, but that's, so we scalar multiply one elliptic curve point h by one scalar, and then another elliptic curve point generated by another scalar. X being the message we're committing to, and R being like the random string that we had in the previous version of the commitment. That's the basic idea. There's a lot of other stuff, and it's actually really interesting, and it's very relevant to all kinds of things, but we can't do everything in one day, so I'm not going to talk about that right now. We discussed this actually last month, but we could discuss it again at the end if you like. Sorry, it's really weird being so close to a screen. All right, so why did I introduce with the commitment scheme? Because the next concept that I think is essential to understand the Schnorr signature is the zero knowledge proof of knowledge. It's a really weird phrase, isn't it? So most people will at least have heard of that, right? Zero knowledge proof. You'll at least have heard of it. Does anyone here feel like they know it quite well, like how zero knowledge proofs work, or you sound like you look like maybe you studied it a bit, but you two get in. Studied it a bit. Yeah, that's how I feel. But maybe the only difference is that I guess a couple of months ago I started to get very interested in bulletproofs, because bulletproofs is this new system for confidential transactions. Do those phrases mean anything to you guys? No. Okay, so I can tell we've got ultra hardcore Bitcoiners and we've got people who aren't ultra hardcore Bitcoiners, otherwise you would know about it. But it's okay. It doesn't matter, I'm going for the basics here. So anyway, that was why I got very interested in trying to understand these ideas, but that doesn't matter to you. So what's going on with the zero knowledge proof of knowledge? Well, we're going to use a commitment scheme as a tool to help us prove that we know a secret, just like, it's not exactly the same as the telephone game with Alice. She's got her heads or tails, but she's got a secret value, yeah? We're going to prove that we know a secret value using a commitment, but without revealing that secret value. It's a very kind of, already quite a strange thing to be able to claim that you can do. But if you've never thought about it before, you should realize, of course, that every time you make a Bitcoin transaction, you're doing that. Sort of, more or less, because you're proving that you knew the private key in order to validate your spending of the coin. Yeah? So it's connected, although not exactly the same thing as a signature. So zero knowledge proof of knowledge. How does it work? How do we use a commitment scheme to prove that we know a secret without revealing it? Alice revealed her heads or tails, so this is a step forwards, right? And it's like another level of abstraction. We're going to have to go up. So this is in words the very vague idea. The vague idea is we've got our secret here, but we're going to introduce actually another secret, just to be confusing. That new secret, which is going to be just a random number, I'm going to make it up. I'm going to commit to that, commit to another random number. Then you're going to give me a challenge value. And I'm going to take that challenge value and combine it in a certain way with my commitment and my secret to give you a new value which you know I can only have produced if I knew the secret. And the kind of general structure, don't worry if that didn't make sense yet, I mean, this is what the next couple of slides are about, yeah? The general structure that I just described to you, where I commit to something, you give me a challenge, and then I give you something back that proves, is called a sigma protocol. And it's called a sigma protocol. It's nothing to do with, well, what am I saying? It's just because of the nature of the interaction being this way, then back, and then this way, and then at the end there's a verify. So it kind of very, very vaguely looks like a sigma when you draw it out as an interaction diagram. Very often they draw diagrams like this with, well, yeah, it might be worth actually having this up on the board for you to think about. Well, they often draw diagrams like this. Yeah? So the prover does something, sends something to the verifier, and then the verifier does something and sends it to the prover, and so on and so on. And the sigma protocol is kind of 3 steps, or there's kind of a 4th step. And it doesn't really look like sigma, but they say it does, so it's a sigma protocol.
Sounds a bit like Diffie-Hellman exchange.
Diffie-Hellman exchange is it's not a sigma protocol, but there's some similarities, and it achieves. I was thinking about that today actually. There's a good comment, but it doesn't actually include that. Anyway, so here's our sigma protocol. Now this is actually an example. It's not all sigma protocols, but it's the example. It's the canonical example. It is the most important one. And I'll tell you what it's called in a minute. So it's basically what we just said. Alice has a secret, X, right? P equals XG. Alice has a secret X. Bob has P, which is the public key, in fact, yeah? But Bob has P, which is the curve point corresponding to X times G. So how does it start? Alice sends, this means chooses randomly, chooses from a random, in fact the set being the set of all scalars between 1 and n minus 1, where n is the curve order. So Alice chooses a random k, sends r equals kg. So notice the pattern here is the same as the pattern there. She's doing scalar multiplication so that r, although it's derived from k, does not expose k, just in the same way as p, your public key, does not expose your private key. So she actually sends R over to Bob. Bob chooses a completely random value E, again from the same set of scalar values, a completely random E. And the last step is simply that Alice calculates, and here we see the equation that we're going to discuss more and more. She calculates K plus E times, sorry about this font, it doesn't work very well, right? But that's a times, and that's an X. Yeah? So S equals K plus E times X. So she takes her original random value K, and takes the challenge value that Bob gave her, multiplies it by her secret value, and returns that to Bob. And of course this is all very nice, but can you see, I mean this is a situation where having pen and paper might help, but can you see why Alice sending S to Bob proves to Bob that she knows the secret X? That's a bit of a difficult question if you're new to this, but what could Bob do with this value S? What can he do with it?
Divide by something, subtract something.
Yeah, that's true, especially if you're trying to...
G.
Yeah, if you're trying to crack this, I would stop dividing and do. But if you're just trying to prove that Alice has done her job, then what you need to be doing is treating this as a scalar multiple of G, because do we need to do this on the whiteboard? I don't know. So can you see, if we put a G here, just crudely, if we just put a G on the right there, and we put a G on the right of everything else, do you see what happens? Yeah? So, taking S and multiplying it, scalar multiplication, by the generator point G is the same as K times the generator point G plus E times X times the generator point G. Now K times G is R, yeah? Mm-hmm. And E times X times G is E times XG, which is E times P.
Sorry, can you repeat, please?
Sure. Maybe we should write it out. If this is the thing I wasn't sure about when I did this talk, is like, if people have done this kind of stuff before, it will be really obvious, but if you haven't, it takes a few minutes to kind of percolate into your brain the idea. Let's go back a step, yeah? So we know the general idea that private keys times the generator point gives a public key. Let's call that A. Notice I'm using capital letters for curve points and lowercase letters for scalar numbers, yeah? So that's true for any, I could write another one, B, G, B, whatever. These are curve points, these are scalars. If we add A plus, sorry, let me write it a different way. If we add these two together, AG plus BG, we get A plus B, obviously, right? But this is this addition is distributive, yeah? So I don't know how trivial it is to prove that. I don't really want to get into that. We can distribute that.
Mm-hmm.
So all the normal rules of, how to say this? Yeah, all the normal rules of multiplication and addition still apply in this context. The only thing you must avoid getting confused about is you can't do things like this. There's no such thing, okay? What we're doing is a group. We've got a group, and a group has an operation defined on it, which is addition. It doesn't have any multiplication defined on it.
Mm-hmm.
Even though we keep talking about multiplication, I'm talking about scalar multiplication. A bit like if you have a vector, you can multiply it by 3 or 7 or 8, like scalar multiplication. Same thing here, because you just add the vector to itself n times, or in this case, add the point to itself n times. You get the idea, right? So that's why when we see equations like this, we can just naturally, we take this scalar equation, it's an equation with only numbers, and we just sort of lift it onto the curve. It's a sort of poetic way of saying it. We lift it onto the curve, we multiply g by each one of those scalars, and then we look at what we've got. We've got sg, well that's a new thing. We've got kg, we've already got that's r. And we've got exg, well that's e times p, right? Now why is that important? It's because these are all public values. Yes, it doesn't really matter that they're public, it's Bob has all those values. Bob, the verifier, has all those values. He has P, that was defined at the start. Bob has P. He has E, he chose himself. He has R, notice he does not have K, that's very, very important, but he does have R. So he can add EP to R, and he can verify whether or not that is equal to SG. If it is, the claim is that Alice must have known the private key X. And that's what we're going to discuss next. Okay. So if we looked at that, because this is absolutely the centre of the kind of presentation, we want to sort of reflect on it. Let's ask one question, like thought-provoking question. What if we remove the first step? Now what do I mean by removing the first step? Remember there were 3 steps, yeah? So removing the first step, what I'm basically saying is, suppose Alice didn't bother to send an R, but only the protocol involved only Bob sending an E, and Alice returning, well, she can't return that anymore, it doesn't exist. So she'd be returning S equals E times X. Now would that be a good idea? Would that be secure? I guess I should qualify that. There are two kind of dangers here, right? One danger from both sides. The danger to Alice is that Bob learns her private key. We must have that the protocol does not allow that, yeah? The danger to Bob is that Alice can generate this value without knowing the private key. So we could call that forgery, yeah? So if we want to make sure this protocol doesn't allow either of those two dangers. So, what am I saying? Yeah, so if we changed it and wrote S equals E times X, where E is just sent from Bob to Alice, do you see any problem with that?
You could just divide S by E and get X.
Right. So we multiply S by the modular inverse of the value E, because this is modular arithmetic, but it's basically the same as dividing. You can do that, yeah. Because it's a scalar, not a point. So Bob would just do that and he would get X. So this version is not secure because Alice is not, she hasn't succeeded in hiding her value. So we can say that the first part of the, you got the answer there. The first part is not, the first part cannot be removed because then without the k in k plus ex, then x is just easily extracted. In fact, you said at the beginning, right, divide, right? That would work there. So k needed for blinding, not the L there, blinding. K is needed to blind the value of x. Well, what about if we remove the second step? That's an interesting question. If instead of doing k, then e, or rather r, then e, and then s, if we did, what would you say? Yeah, second step. If Alice generated a K and then sent R equals KG, sent R to Bob, and then Bob didn't do anything at all, right? And then Alice just said, well, you know what? S is K plus X. And she sends S, yeah? So she sent R and then she sends S. There's actually a non-interactive protocol here, so it'd be really cool if it worked, yeah? I'm just going to send you R and then send you S. What's the problem there?
But Bob won't figure out that she had to new X.
Yeah, I think you may have improved on my answer there, yeah. If no, that's not my Think properly. How does Bob verify?
Well, you can't know that she had to new X to do it.
Well, it's true, but you need to explain why that's true.
Because she could send any random number. I can't get K.
Well, what would Bob's verification step be?
Get K out of R, which...
No, because Bob never gets K even in the normal protocol. He gets R, right? So we're probably talking at cross purposes. What I'm saying is that Bob would do that. Right? So it's not like it would expose K or something. So he would take the S, multiplied by G, he would take the R that he's been given, and simply add it to the P, which is known at the start of the protocol, and check if it's equal, which would be valid mathematically, but the problem is that because Alice wasn't forced to get S after an interaction, she's able to do something like this. She just makes up, first of all, she makes up an R dash, for which she knows the K dash. Then she subtracts P from the R dash. Right? So this is what we call a key subtraction attack. Yeah? And it means that effectively, when he checks SG equals R plus P, he doesn't realise that Alice did this, R equals R dash minus P. And she knows R dash is K dash G, right? So therefore, when she puts that in there, it just becomes R minus P plus P. So P is irrelevant now. So she's forged the proof. She's forged the proof that she knew X by subtracting X out of the equation. And she can't do that if we include this second step of a challenge. That's why it's an interactive challenge. Yeah? So K protects Alice, E protects Bob. I mean, you can do a lot more sort of thought experiments about this, but and it's not like it's the only way of achieving this goal, but maybe it's the simplest. I'm not even sure about that, but yeah. Okay, go on, question, Tim.
Who held down this protocol?
The Sigma protocol?
Yeah.
I can't remember. It was a long time ago. I'm willing to bet it was a paper sometime in the 80s that came up with this general concept of a Sigma protocol, but I think I did know at one time, but I've totally forgotten. You know, Google. Don't go. Yeah, no, don't go. Don't say Google. I reject Google. Anyway, but yeah. But actually, what we just talked about is not. I want to be clear. Is not the Sigma protocol. It's the Schnorr protocol, which is one example of a Sigma protocol. Yeah. The Sigma protocol concept is more general, and it just means any time you have this pattern: commit, challenge, response. When I was looking at bulletproofs, this was sort of clear to me because it was showing me many, well not it, but the kind of academic background of bulletproofs has several examples of the same structure but like more complicated. Maybe you have several commitments, and maybe you have several challenges, and so, but it's the same pattern. Isn't it? So what we just looked at though is the specific example called the Schnorr identity protocol. An identity protocol because it's Alice proving her identity in a way. She's got some private keys that represents her identity. You know, it's a bit like a password, right? And so she's proving she knows the secret. So, yeah, it's all very nice. But so now the next few slides are, what about security? So to talk about the security of this construction, we need to talk about the definition of a zero-knowledge proof of knowledge. So I think this is quite self-explanatory, I hope, because it should be fairly obvious we can keep in mind, okay, this is a very abstract term, zero knowledge, proof of knowledge, but we can just keep in mind that example we just looked at. Somebody's trying to prove they know a secret. It could be more complicated than that, but let's just keep it simple. Obviously, it's necessary, if I do know the secret, I should be able to prove it to you. Equally obviously, it's necessary that if I don't know the secret, I should not be able to. So that's these two definitions here, completeness and soundness. Completeness is always really kind of trivial to prove, because it's just like saying, does the equation actually balance? It's really all it's saying. If we wrote the equation wrong and it was S equals K plus alpha EX, nobody knew alpha, then we can't produce an answer, so it's not complete. Soundness, it will turn out in a minute, even though it's just like the flip concept, is actually much more difficult to prove. It's much more difficult to prove that I can't forge the secret. And zero knowledge is a really wacky one, and a really crazy one, which is saying, not only am I, not only doesn't apply, I'm going to prove it to you, but I'm not going to reveal any information in doing so. So you can easily imagine this is absolutely critical with the digital signature scheme if we're going to use it for a cryptocurrency, right? Because, well, hopefully we don't reuse addresses, but if we did, or if we do, and we start making lots of signatures on one key, and if somebody can get any information from that at all, it could be a complete disaster, yeah? So that's a kind of concrete example of why this concept is so important, but it's got much wider applicability than that. So we want the proof to reveal absolutely nothing other than one bit of information, which is one bit, right? Either I know the secret or I don't. I was thinking about that today. What if I know half the secret? Have I revealed half a bit of information?
Then you don't know the secret.
Well, okay, true. Yeah,
like you know that the first bit is zero.
Yeah. No, I mean that's a serious point though, because I remember reading about, if you have some non-randomness in your nonce generation, then you have these kind of lattice attacks, and you could end up, getting just like from a tiny, like one bit of non-randomness, you could get the secret, and I don't know. But anyway, the concept is.
It wouldn't fit under the definition of zero knowledge anyway, because it has to be binary.
Yeah, it wouldn't. Right. There's maybe some other word for it. Yeah. Okay. So this is the really wacky part, and if it doesn't make sense to you, just join the club, okay? Because I know even like really super duper ultra smart people who told me it didn't make any sense to them either. No, not this, but the idea. But think about it for a while, maybe it will make sense. So to try to prove that the proof that we have is sound, in other words, that nobody can produce the proof other than the genuine owner of the secret, we need to imagine the prover as being kind of constrained or isolated. You can think of the prover like just a program, an algorithm. Yeah. So, obviously in real life, usually the prover is an algorithm controlled by a human who happens to know the secret, right? But you can think of it like a function or a piece of code that contains within it the secret and follows the steps, commit, challenge, response, whatever, and produces the correct answer and passes the test, so to speak. So we imagine the verifier trying to extract the secret, because the idea of the soundness proof is that he can't do that. So imagine that, can he cheat can he extract the secret if he cheats? And I've written here cheats can only mean cheats with a prover that executes as normal, but we create different provers in different universes. Which sounds ridiculous, but I've heard it described different ways, but the way I really like to think of it is, the prover is sitting there, maybe it's on my computer, right? It's just a very small function. Inside that function somewhere must be the secret, because it couldn't, well, that's what we're trying to prove, is it can't produce the correct verification if it doesn't, the secret's not in there. So what if I'm a programmer and I start running the prover, but then I use maybe breakpoints, I debug it, I go to debugger mode, and maybe I make a second copy of the program, yeah? Nothing's stopping me doing that. And in the literature, they usually describe it in terms of actually even rewinding and going back to an earlier step. But I prefer to think of it as making two copies and going forward one step in one copy and keeping the first one earlier on. So In other words, think of the prover being isolated as a program that we can control. In that scenario, can we extract the secret from that prover? Any thoughts?
When you reach the secret from RAM or somewhere.
If it's deterministic, you could.
What's that?
If it is deterministic, then you could.
Huh.
Like everything that's deterministic, you can just go back.
No, but if the program's rules are something like, see if we can actually like say it in words. The program will do something like, step 1, generate a random K, right? Produce R and output R. Step 2, on input, because it needs input, so it's not one. On input of a random number E, calculate K plus EX, output S. So there's a set of steps there. Now parts of it are not. Parts of it don't have to be deterministic because you generate a random number K. But I'm not sure that's getting to the heart of the matter. The point is that if you can run 2 copies of it separately, like so you can get the prover to make his commitment. So remember our commitment is R, the value at the beginning. Do you remember you know what, I think to make this clearer, we need to write not this stuff, but the actual 3-step protocol. So it's in our mind as we do this. So the 3-step protocol is prover chooses K and sends R to the verifier. The verifier generates E and sends E to the prover. So that's not very clear, is it? R is being sent and then E is being sent. And then S equals K plus EX is calculated and S is sent. And the verification, remember, was SG equals R plus EP. P equals KX, XG. So what I'm saying is, P commits, what does that mean? It means P generates K, sends R. P's done step 1. V branches the universe. So you can think of that as just makes 2 copies of the program at that point. Okay? He sets the breakpoint. He stops the program after the sending of R. He makes 2 copies. Right? And then, challenges in both. So now, instead of this flow being one flow, there's now 2 flows, right? There's a second flow where after that point there's a second flow where he sends a second E, and the prover, following its algorithm, right? The prover following its algorithm will calculate a second S, and it won't be the same. It won't be the same because although the K is the same, because the commitment step is the same, and the X is the same, the challenge is different.
It's like the using all values in Bitcoin.
Exactly.
So you lose the secret.
Yes, exactly. Which is the point of this weird, incredibly weird argument. Okay, so you imagine it like the prover is just a program, dumb program, doesn't know what it's doing. It's got a secret inside it, which I represent as a dollar sign there. That's the secret. And I, as the cheating verifier or extract, we call it an extractor, has total control of its environment, right? And so stops it, copies it, runs it twice. Running it twice, we extract the secret by. Sorry, I'm just glossing over that because he already knew, but you guys probably didn't. So if you think about it, it's very obvious that if you do this protocol twice, well, I'll use without a subscript. If you do this protocol twice with the same K value and the same private key X, you can trivially extract X and do K because you can just, you can see from algebra, right? Just take one equation away from the other. Subtract S from S2, cancel equivalent, E2 minus E times X, divide, we get X, right? So this is a very well-known weakness, both in Schnorr and ECDSA, which is that you can extract the private key if you use the same K value, which we call a nonce. I didn't use that word. If we use a nonce twice on the same private key. Yeah, notice it doesn't matter. Well, that's another discussion. Is that clear? Yeah, so what does that mean? Well, it means that if we could control it like that, we could extract the secret. Agreed?
Yeah.
Now we can't control it like that, because if we could, this whole thing wouldn't work, right? Because then I could, every time you sign the thing, I could just take your private key, because I control you. But I don't control you. So what the hell am I talking about? Why am I saying all this in a scenario which is not real, right? There's no God, there's no controlling of the prover. What does it prove?
It proves that X is known by this machine.
Exactly, yes. It proves that X is known by this machine. So the way I put it when I was writing on this bulletproof thing, I said, imagine you had $100. God can steal $100 from you, right? Because he's omnipotent. He can do anything. But can God steal $100 from you if you don't have $100? Even though he's omnipotent, he can't, right? He could imagine $100, put it in your pocket and take it out, but then he wouldn't be stealing it from you. So that's the basis of this argument. The basis is that you can only extract something that is already there. So no matter how ludicrous the setup, no matter how ridiculous the setup of the proof is, the fact that the secret comes out means the secret's in there. So what this does is it proves that that protocol that we described does actually have what we call knowledge soundness. That means it does, it is impossible to forge a signature. Forge the identity of Alice. Does it make sense?
No.
No, okay. It's normal. I think he got it because he got the right answer at the end there. I think you probably, but they've been looking at this stuff before, related things before, so it's a lot easier for them. If you have a question, I'm more than happy to try and answer.
So if I use K, which is like 1 or 2 or 3.
Yeah, that's an interesting question, that. Well, if you do that, you're exposing, it's your failure as not choosing properly.
I still, even though I use a K which is unique, by mistake my random number picks a super low one.
Yeah.
Someone can try
You could ask that question about private keys. I mean,
if they try brute forcing, like, I'm going to try K equals 0, try K equals 1, and then maybe.
But that's the same as private keys, right? You know, if I generate a private key, I mean, K essentially is a private key. It's just an ephemeral private key. We just use it once and throw it away. So it's the same kind of security scenario. Are you guys familiar with the term nonce?
Yeah.
N or N1s, yeah. So that's what we're talking about.
It's N1s.
Yeah, well, if you speak to Adam Langley at Google, he always says N1s because he knows that in England, nonce has some other meanings. Yeah. N1s is a better way to say it because that's what it means, N1s. Yeah. You know, this is also weird, but it's like the opposite problem. Now, I just want to remind you what we were doing is we were saying, where's the start of this? Oh, sorry, I've gone too far. There it jumps. So we showed how to prove soundness, very vaguely, but we gave the general idea. Zero knowledgeness, we want to prove now that doing this protocol, Alice doesn't reveal any information to Bob. It's very, very important. And I'm really just going to very sketchily talk about it. So, how does this work now? Yeah, so it's kind of the opposite, but it also kind of isn't. So what we want to do is produce transcripts of the protocol that look as if they're genuine. So what am I talking about? Transcripts, protocol. So think of this as a conversation between prover and verifier, or Alice and Bob. P says R to V, V says E to P, I'm getting lost. S says, B says S to B, you get it right. So you could summarize this as R, comma, E, comma, S. Yeah. Those are the things that are exchanged, right? And we can call that a conversation that the prover and the verifier have with each other. And this is a transcript of the conversation. This is just these three numbers, okay? So the question now is, but it actually isn't obvious that this is the question, but this was like the great insight, I think, of the original zero knowledge paper, which was Shafi Goldwasser, Mikali, and the third one I always forget. Anyway, it's like really a long time ago, mid-80s, ages and ages ago, they came up with this idea and they said, well look, imagine you had lots of different protocol executions, you get lots of conversations, right?
With the same private keys.
Are we talking? Yes, yes, I'm talking about the case where you just keep doing it with the same private key. Now, it doesn't follow, by the way, that if you do lots, you get this problem. No, you don't get that problem unless you make the mistake of using the same K. Because notice here, if this was K2, no problem. Think of it in terms of algebra. This is kind of important.
Yeah. What happens if?
Look, how many unknowns are there here? Look, we don't know K, we don't know K2, we don't know E. Oh no, sorry, we do know E, and we don't know X. These are unknown.
Is it possible that, so every time you generate a new key, right?
Yeah.
What's the probability of generating the same key again?
Okay, so there's a couple of answers to that question. Well, I'll let somebody else talk for a minute. Go ahead.
It depends on the number of bits.
It depends on the space on the group you're using, because it has to be a scanner. So if the group is size 256 bits,
Yeah.
then it's 2 to the 1 or 2 to the power 256. But if your group is tiny, then it's tiny.
Yeah.
When Bitcoin is
So
1
the
over 2.
group on this is an N number, I think, isn't
Yeah.
it? So that's
Slightly less than
2 to the 256.
It's the same argument as for the hash functions.
Well, but it's the same level of security you have with private keys.
Yeah,
When you generate private keys randomly, you can generate as many addresses as you like in your wallet. Nobody's going to tell you, oh, you might accidentally collide. It's not going to happen.
It's not incremental. It's not like you have like like 1, 2, 3, 4, 5.
It's like the edge of the universal size. It's ridiculous. So, okay, yeah. So notice that the normal way things work is even if you make two signatures, or in this case, conversations, with the same private key, as long as you use different Ks, you're fine. Because you have 3 unknowns and 2 equations there, notice, yeah? And then it will be K3, and then it will be 4 unknowns and 3 equations, and it will always be overdetermined. I always get that wrong. Overdetermined? You know what I mean? You can't solve it. So conversations like this, and the idea that they had in this paper was, if we make, well, in normal operation, we would just make lots of these conversations. Notice it's interesting that the values in the conversation are all random numbers. Even though that one's a point, not a scalar, it's still a random value. This is chosen purely randomly. So if you make lots of conversations, that's one thing. But what if you forged lots of other conversations that looked similar? Could you do that? Could I make another conversation, R-E-S-, in such a way that it would look like it was a proper conversation to an outsider, or to an outsider, or to the verifier. Yeah. Well, anyway, is it possible to do that? Is it possible?
Do you mean and also convince them that the proof is valid? Like.
Well, no. The reason there's a confusion here is because we're talking about an interactive protocol. Yeah. If you and I engage in the protocol we've just discussed, I can prove to you that I have no private key. But if you take the conversation we had and gave it to someone else, it doesn't prove it, does it? Because you had to be the one that chose the challenge. Yeah, you had to be the one that chose the challenge, exactly, right? So that kind of intuition is the basis of this. What they said was, okay, if we can set it up so that we can create a whole set of conversations that look valid specifically in the sense of that being validated, yeah, then it must be the case that no knowledge is exposed. Because if an adversary, an attacker, can make lots of conversation transcripts that look exactly the same, at least in distribution, obviously they're not literally the same, but in terms of distribution, the same as fake transcripts, then he can't be receiving any information when he receives real transcripts because he doesn't know the difference, right? So that's the argument. It's a very weird argument again. I'm sorry, 2 weird arguments. But how would it work in practice is we have the notion of a simulator, somebody who simulates these conversations. And the simulator, all it needs to do is work backwards. That's the trick. Because this is what makes this work is kind of causality, the fact that I can only do that after you did that. Yeah? But if we can kind of violate causality, if we can just create S at random, right? Randomly. Then create E at random. What would we do next?
Solve for R.
Solve for R. We can solve for R, as it happens, if you just look at the equation, because it got S and got E, you can do SG minus EP, and you get R. Notice, interestingly, you don't get K, but you do get R, and that's all you need to make a conversation transcript that looks like a real one. So if I can make an infinite number of fake conversation transcripts that look exactly the same to an attacker as real ones, he can't possibly be able... sorry, I should qualify. Look the same, I mean statistically look the same. Obviously not the same numbers, right? So you can make lots of R's, S's and E's that are, if the distribution of fake transcripts is indistinguishable from the distribution of genuine ones, it, in quotes, proves that zero information is conveyed. What distribution are we talking about here? What statistical distribution are we talking about? Exponential or uniform random, right? It's just a uniform random. I mean, in theory, I'm not going to try and prove that, but you get the idea.
So are you saying in the proper proof for this that statistics comes into it? Like
I think it could, but I don't remember. I tend to sort of glaze over a bit when I get to that level of detail when I look at these proofs and descriptions. But I did note that, at least for this one, we're talking about a uniformly random distribution. There might well be cases where, but it wouldn't be like distributions like exponential or what's it called?
So it's more like
Poisson, something. Yeah.
So from one x, I can basically make from one x, I can make any s given.
You don't need x.
No, I mean from a secret, I can basically, if I try to do it, I can create any s. I just have to find the correct E.
We're talking about where you don't have X.
It's just it means that there's like as a prover, I can basically from a prover's perspective, I can create any number given the right E. Because it could be that if it's not the case, if I make the E, if there's two classes of stuff and I'm making information even. To explain it. If I can't make numbers with my x, then I know that it's let's say positive x cannot do this range of numbers. Then if I cannot make a proof which is in this range, I mean I have a negative x. So it means like there's a bijection of x to s.
Okay, like you're trying to figure out the right way to sort of understand how the distribution is random and...
if it's not random, then if I make a thing...
I mean, it's kind of obvious, I mean, at some level, but
it's not just
going into the mathematics,
which is clean
proofs. I think it's fine, we don't need to go...
Could you put it this way? Could you put it this way, that you can have all these transcripts, real transcripts and fake transcripts, but there's no way to convince someone that transcripts is fake, and therefore there's no knowledge. Like I think there's knowledge inside, so that could be another way to put it.
Yeah, absolutely, I think so.
The fact that you can't convince someone that it's fake,
yes.
and it could be real or fake.
You can't convince you can't distinguish. I mean,
it's indistinguishable.
So this is kind of an annoying add-on, but it's really vitally important in practice, which is what's called the Fiat-Revere transform. So we've been talking about Sigma protocols, and specifically the Schnorr protocol, the Schnorr identity protocol as an example. If we want to make it non-interactive, because it's no use just having protocols where I prove to Chris, and I prove to you, I prove... That's rubbish, We need something where I can prove and make the proof transferable. Just give it to the whole world, everyone can see that I know the secret. To do that, we need to make the protocol non-interactive, to remove this step. Okay, and we just spent hours explaining why we need that step, so how the hell does that work, right? That's what you're thinking, which is a good thought. But the way we do it is very ingenious. We use, again, a hash function, or... Is there any other way to say it? But I think we should call it a hash function in the sense that we take... Oh yeah, of course, we need a random oracle is the more technical term. But let's just think of it as a hash function. What we do is we hash the conversation up to the point of the challenge. Now in this case that's very simple. And that's just the value R. So we're going to hash the value R, and we're going to, by doing so, we'll create a random value output which we could not have predicted. And because we could not have predicted it, we can't cheat. Remember we had that problem where, what was it now? We had the problem that if you, am I getting this right? If you removed this step, we found it was not secure because we had k plus x, and then you could subtract the public key easily. Yeah? But if you hash this, you still actually do get a number here, but it's not a number you can predict at the start. That's the key. Because remember the attack, if I just remind you, the attack was to define r prime equals k prime g, and then set r equals r prime, minus p. So you would have to, sorry, that's stupid. That attack doesn't apply because there is an e here, right? But the point is we don't know the e in advance, so we can't do an attack like that to get s without knowing x. So this, I'm trying to give you a really concrete explanation of the concept. The concept is to hash the conversation up to the challenge and make that the challenge. And that's something that Alice can do on her own. Bob doesn't need to be there. She just hashes R.
It's like simulating that step.
Exactly, it's like simulating, yeah. It's exactly like simulating the challenge. Yeah.
In a bounded way, like you only simulate one thing. From one R, you only get one E.
Yeah. Well, that's an interesting question, actually. I'm not sure that follows.
And in digital signatures, the E also contains the message.
Yeah,
change it now.
Next slide. Next slide. But that point you just found, I think you're wrong, but that's an interesting statement. Anyway. So now the Schnorr signature. What is it? It's exactly that. What we just discussed. Using specifically, it needs that Fiat Schnorr trick, because otherwise we can't make a signature to make it non-interactive. But also, of course, a signature is on a message, so we have to put the message somewhere, and we include the message in the hash. We may or may not, it's better if we do, also include the pub key. It doesn't actually hurt, if you think about it. You can put anything in there. So we put our message that we're signing. Sorry, this is should be a K. I apologise, that should be K. Remember K plus EX. That's E now. So our E has changed from being a random number to being the hash of the message, and crucially, the point R, and possibly the point P. So now we've changed our identity protocol into a signature scheme, and that's just saying in words what we just said. Hash one way, and this enforces. Yeah.
What is the hash?
Good question. I'm using that to represent concatenate.
Okay.
Yeah, so I think people usually do that, but for some reason I decided to do one, sorry. So M and P and R are all hashed together. Yeah? Yeah. Okay, so we've got most of the theory stuff out of the way. These next kind of few points, a bit vague. We talked about zero knowledge, but we didn't really talk about the fact that that proof is really limited. It's what's called honest verifier zero knowledge, because we're assuming that the E value, the challenge given by the verifier, is actually just random and not deliberately like malformed in some way.
Because if I say E equals 0,
well, I
think that's not allowed.
You're thinking of RNS not being able to be 0 in ECDSA, right? But probably, whatever. Good luck finding 0, but good luck finding a hash which is not random, right? Anyway, that's, what's on here? Simulator gets the cheat, yeah. Yeah, so the way we kind of get around the fact that all these proofs were based on interactivity is we kind of pretend that, or we kind of program the random oracle, so that the hash function is what's called a random oracle. Does that phrase mean anything to anyone, or should I try and explain it a bit? Random oracle?
If you could.
Yeah, just crudely, it's like, well, forget about hash functions for a minute. Our task is to create something that creates a random output given any input, but does it deterministically, right? So imagine I am the random oracle, you give me an input, you say the string hello, I turn around, I've got this massive table, and I write in my table, hello, output, 03647, blah, blah, blah. Well, you've got it already, right? So the point is, if anyone else says hello, I'm going to respond the same thing, but if somebody says goodbye, I'm going to make up a new random value. So if you think of it, a hash function is an attempt to create that effect using some mathematical tricks, right?
Is the hash function secret? Are you announcing what the hash function is?
Are you talking about this explanation of random oracle? What I'm trying to get at there is that when they go through all these security proofs, they use this concept of the random oracle model. And the thing about hash functions is they're actual concrete mathematical functions, right? And we don't know for sure that they behave exactly the way we intend them to. So from a theorist's point of view, they define a random oracle as like an ideal of what the hash function should do, which is to output deterministic random values for any input. And in terms of secrets, there's no secrets involved really. It's just that you can't predict what the output will be given the input.
But if you're able to calculate the output because you know the hash function.
Oh yeah.
But does the person who's giving you the input
No, you're right.
know what the hash
It's just the
function
same
is?
as any hash function in that regard. Anyone can do it. Yeah,
Okay.
the person can do it in advance. The point is because they can't predict the output, you get this kind of forced causality effect. So the simulator programs around an oracle, and I don't want to go into it because it's boring. Basically, program the random output to output the E that you want it to output in order to make this proof kind of still work, even though we're not interacting anymore. It's kind of dodgy. I mean, there's Matthew Green's got a really good blog post, 2 blog posts about zero-knowledge proofs. In the second one, he talks about this and how it's kind of a really dodgy proof. But I mean, I'll let the experts kind of argue about that. So quickly, just going over the idea. What kind of security do we have? We have some concept that all of this is sort of secure. We kind of half proved that you can't forge it and you can't extract the private key. Yeah, but it was all based on a very basic assumption, right? Which is that the very first thing I wrote on the whiteboard, if you remember, was P equals XG, right? And we said, it's a private key and a public key. We all know the idea is you can't get the X from P. And so in the elliptic curve context, that's called the elliptic curve discrete logarithm problem. Because it's the problem of extracting the elliptic curve discrete log of P, which is X, given only P. And it's not impossible, but it's because you could simply look through every possible value of X and you could find it. Right? So we call that computationally hard because we don't have algorithms that calculate it quickly, I think.
Is that a one-way function?
Yeah, we treat it as a one-way function, but what I'm noting at this point is it's not perfectly true, right? It's not, given enough computational power, you could find the input simply by exhaustive search. And there are algorithms, I think, that allow you to do it. Correct me if I'm wrong.
Schnorr algorithm with quantum computing.
Which one?
Schnorr
algorithm. Okay, well, I'm not going to go there. That would just blow all this out of the water. Because ECDLP is lost to a sufficiently powerful quantum computer. I don't know. But I was about to say that the algorithms are about, aren't they like square root n time?
They're exponential time. So we don't have a polynomial time algorithm. We have a polynomial time on that way, but on return we have an exponential algorithm because we need to simulate all of them. We need to try all of them.
Yeah, but isn't it like root n? Doesn't it work out to be like 128-bit security because you?
Yes. So that's square root of
square root n, isn't it? Yeah. But anyway, that's another topic. Let's not get lost.
But it's still exponential in.
Yeah, I know what you're saying, yeah. Because it's in the power, it's not in the, exactly, 2 to the root n, not root n, yeah. Thank you for the correction. It can be shown that if an attacker can extract the private key from it. So this is a big part of what I was aiming for with this, was it? I don't know, maybe with this talk was like, can we at least get some inkling of why this makes sense? We can say, under a certain set of assumptions, that if the elliptic curve discrete logarithm problem is not cracked, in other words, solved in sub-exponential time, as you say, then the Schnorr signature is secure. That's the claim. And the claim is based on really arguments that are along the lines of what we've just discussed. So this part is easy for us, right? If you have an adversary that is able to crack the signature scheme, now imagine you have an adversary that basically with one of these type of protocols can extract the X just from being verified and looking at it, let's say. And let's say you're able to do that with probability epsilon. So you're not going to win every time, but you're going to crack it one time in 10, let's say. Right? So 1/10. If we have such an adversary, that adversary can crack the elliptic curve discrete logarithm problem. Sorry, I've confused myself, haven't I? Yeah, that doesn't surprise me. I was a bit confused about this. I was trying to argue that, I was trying to point out that the attacker can extract the secret if he can if you can forge the signature? I seem to not really know what I'm talking about here. Excuse me. I was looking at this the other day and I seem to got confused. Yeah. Impersonate the holder. Yeah, that's a subtle distinction, isn't it? Yeah. Yeah. Yes, of course. Yeah, I'm being stupid. Right, I get it now. Do you get it now? So there's two slightly different things, right? Here's a Schnorr signature, right? And I claim I'm the holder of the private key and I can make a signature. So if I can impersonate, let's say Chris actually holds the private key and I don't, right? If I can impersonate Chris by making a Schnorr signature, it doesn't necessarily mean that I have the key. It might just be like there's something broken, right? But if I can do that, what this argument says is if I can impersonate him, it means I can solve the elliptic curve discrete logarithm problem because I can extract the discrete log by impersonating twice the same argument we used before, where if you end up using two different challenges on the same commitment, you end up being able to extract x.
You just need e squared.
Yeah, it's just the only detail, the only reason I really wrote this out is because it helps you to observe that in fact, roughly, this is not exact by any means, roughly, your chance of success in extracting the discrete log is the square, so that means less. Yeah? So instead of 1/10, we're talking 1/100. Yeah? So they talk about these kind of arguments as security reductions, like saying, what is it now? Yeah, saying the signature scheme is secure because we can't solve discrete elliptic curve discrete log. It's really weird. I find this argument really weird. It fascinates me. It's like, well, if the signature scheme was not secure, then I could do this, and I could solve ECDLP. Now, I don't think anyone can solve ECDLP, therefore the signature scheme is secure. Did you see? This is what they call a reduction. Yeah.
It's like you're proving the equivalent problems.
Yeah.
So if you can solve one, you can solve
But
one.
then the annoying thing is they're not literally equivalent, are they? Because
No, they're...
yeah.
Oh,
Yeah.
now I get it.
Yeah, you get it. It's really like
So reduction, like you have all the complexity classes like P and P.
Oh, right.
So like in the non-deterministic polynomial classes, which are NP problems, and we are simulating them in exponential time nowadays. So you have the concept of reduction.
Right, same thing.
So what means that if you solve if you solve one problem in an NP class and all the problems are have the property of reduction, that means that with one problem you can solve all of them. So yeah, like it comes from there.
Yeah.
Like sure, 100%.
Oh, sure. Okay. Yeah. So. Yeah, as you can see, I was confused because I'm really not very clear about that stuff. I haven't studied it properly, whatever. And also here, I'm not sure if I've got much to say about this. I was kind of reading about, what is digital signature security, and there seems to be a lot of different concepts. It kind of does make sense, but I think this is getting kind of complicated now. Like, you could talk about obvious things like, is the signature scheme secure against somebody just extracting the private key? But also, is it secure against forgery? Also, is it secure against forgery if I've already got several examples of a signature? Also, is it secure against forgery if I manage to do several signatures in parallel and they go on this list? But I don't really know much about all that stuff.
You need to be secure against all of those.
Yeah, yeah, absolutely. I think I noted here in bold. I think this is the strongest definition of security. Security against existential forgery and a chosen message attack. So if I can get you to output signatures for messages that I choose, you still can't create a new signature. Existential forgery, I've forgotten what that means. Existential forgery. Anyway, you can look it up. I don't really know. So I just want to make a few notes about ECDSA, and for this is one of the reasons I needed a whiteboard.
Can we open a little bit more?
Yeah, I it's crazy, isn't it?
Stop.
think it was not bad. I think it was not bad. No, it's due to
You close
is it slides?
Yeah, I didn't like it. Slides.
it. Bad design, anyway.
Okay, so we're familiar by now with P as the public key. I'll stick to the same notation. X, private key. K is N once. Right? And for ECDSA, we have a very different, we have a different equation for the signature, which is, anyone want to tell me? It's my teacher's coming back here, I'm in my teacher mode. Anyone want to tell me? Really? Wow. There we go. Well, yeah, you could reverse it, right? Yeah, we need the hash of the message, right? Plus, now this is where it gets interesting. R times private key. And we publish the signature as two values, R and S. So I kind of obfuscated that the Schnorr signature we publish either as E and S or as capital R and S. Okay, but we might come back to that. So this is an ECDSA signature, and what is R? R is actually the X coordinate, strangely enough, of R, where, and here I'm using the same notation as in the previous things, right? So we take our K, we make an R, just like Schnorr was saying. But we then do something very different, which is that we take the X coordinate, because every point on the curve, like P or something, is an X value and a Y value. We take the X coordinate.
This is the random record.
Yeah, but that's, I think, I was trying to research this a bit, but I think that's the fundamental problem with this. Well, no, there's two problems. So one problem here is that, yeah, so now I hope you can see that this corresponds, that if I take the signature that I've been given, I take the modular inverse of it, which is annoying, I multiply it by the hash of the message times G, plus the X coordinate of the R value, which is actually published as part of the signature, multiply it by the public key, and then take the X coordinate, it should be equal to R. Yeah? So that's how we verify a ECDSA signature. So you can see the formula is more complicated. It uses modular inverse, either when you're creating it or also when you're verifying it. And it also does this very weird thing where it takes the X coordinate of a point. So there's kind of 2 or 3 different things that are a bit strange about it. This was created, I think, in 1992. It was created because shortly before that, Klaus Schnorr had patented the Schnorr signature. And so, yeah, the simpler version that we've just studied, they were not able to use it, so they had to use a different formula. Now, I don't know how they came up with this exact form. I'm sure it has some good properties and some bad properties, but I'll note a couple of bad properties. Firstly, because R is an X coordinate, this may not be immediately obvious, but there's going to be 2 points on the curve with the same X coordinate. This can be explained easily without thinking about pictures, just because the formula for our elliptic curve is that. So given a particular X, because of this square here, we have 2 different Y's. Right? So we have 2 different Y values. So we have 2 different points, X, Y, and X minus Y on the curve, for which this verification is possible, because all we're checking is an X coordinate then. So that creates what you might call an intrinsic malleability in the curve. And that means that, in the signature scheme, in the signature scheme, because it means that if RS is a valid signature, so is R minus S.
Does this only debate like canonical R values?
Yeah, so BIP 66, if I'm remembering that right, yeah, the one that was that fixed the low S. They call it the low S. No, high S is non-standard, right, and low S. So it doesn't really matter, right? It just means that only one of these is kind of standard in Bitcoin now. So if you have some really old wallet, it might generate signatures which don't broadcast properly on the network. And it's just because ECDSA fundamentally has that property. You can't get around it because it's using the X coordinate. And that's one problem with ECDSA, but you could argue it's just a technical problem. Well, no. I think cryptographers also have a serious problem with that because it's a bad property for a signature scheme to have. You shouldn't have a situation where, given a signature, I can make another one that's actually different, even though I don't have the key, right? It's kind of not desirable. Now the security reduction, which we mentioned on the previous slide, I've tried to find out exactly the situation. As far as it's difficult, but as far as I understand it, the cryptographers are not able to find anywhere near as clear a security reduction for ECDSA. And it makes sense because of this weird X coordinate thing. Yeah, I'll say that, but I'm not really sure what I'm saying there. All I know is that I've heard that it's a lot more difficult problem. I have a couple of links if anyone's interested, probably not there.
Because the safety of Bitcoin shows that it actually works.
Yeah, that's a good point. Yeah. I think that's a very fair point. Yeah, maybe it depends on the way you use it, and if you change the way you use it. I mean, if we're in a position of not knowing, then obviously it's not good. I'm not trying to claim that the Schnorr signature is like perfect. It's just that given a certain set of assumptions, it seems that you can construct a very elegant proof. As far as I know, again, I'm slightly beyond my level of knowledge here. But I do want to mention this, no linearity. So what I mean there is that if you look at that equation, it's very nice and linear. If you add the two equations together, because there's no like non-linear terms, you can just add those two, add those two, add those two, and you get something that's consistent. You know, linear as in FA plus B equals FA plus FB, in that sense. Yeah. So that's going to crop up now. What time is it? Because I know that this is a very big presentation. It's very tiring to be sitting in such a hot room, and I don't want to. It's 8 now, so we've been going for about an hour and a half, I think. Yeah, a bit longer than I hoped. Sorry about that.
It's a nice lesson. So.
It's what?
It's a nice lesson. So.
Okay, great. I'm glad you enjoyed it. Yeah, as you can see, the last few slides, I'm not really sure what I'm talking about quite so much, but I thought I'd put it in there because it's really important. So. Okay, maybe we'll just like do one application, and then if we get tired, we can just take a break or stop. So it's linear, right? So we're just saying that, both in the nonce and the key. That's nice. Suppose we add signatures together. Yeah.
This is like the signature aggregation schemes for Bitcoin.
Suppose we add signatures together. So I'm going to do a signature, Chris can do a signature, or Alice and Bob, whatever. Add them together. We can clearly see we're just going to be adding our nonce points. Well, we won't know each other's nonce points, nonce values, but we'll do that. And adding our private keys without knowing them. Now, E has to be one thing. For that to be linear, if you think about it, the two E's can't be different, right? So we could make the E be, instead of R and P and M, it could be the sum of our R values, the sum of our public keys, and the single message, let's say, if we're signing the same message. Well, this is insecure. And it's insecure for a reason that it's insecure for a reason that we kind of touched on right at the start. I'm guessing some people know this story I'm about to tell. Why is that insecure?
Isn't it a computer signature like a subtraction thing? Where I can compute a signature that basically I put nothing in and I just get your key back.
Yeah, anyone else?
So you can choose, so Alice can choose her public key to cancel out Bob's public key.
I'm sure that's what you meant, but it wasn't so clear. But that's right, Chris. Obviously. So if the keys produce, why did I say that? Well, yeah, of course what I mean there is if
I notice it,
yeah. If obviously this attack only applies if we don't already have the public keys fixed in advance, or if the verifier doesn't know the separate public keys. But anyway, just generally speaking, that's not a secure approach because we can subtract other people's pub keys. So if we go, maybe the obvious example, we go around a room, we'll add our public keys together. The last person can make a public key that subtracts all the other ones, which is rather annoying because then he can just spend the multi-sig on his own. It's supposed to be 5 people agree, but he just does it all on his own. So that's terrible, absolute disaster. rubbish. So cutting out all the stuff, I'm going to give you a couple of links in a minute, because I'm not going to explain it all now. But cutting out all the stuff, you end up, if you want, this is called key aggregation, right? What you want is to make a signature where you publish on the chain, on the blockchain, only one public key. And that public key, I'm calling the aggregated public key here. Yeah. But in order to do that, what we're going to have to do is interact with each other, unfortunately. We're going to have to interact, share each other's R values, and share each other's public keys, and then build this rather complicated equation for the signature. Okay? And what I'm drawing here is actually, what I'm writing here is specifically the construction that they're calling musig, if I'm getting that right, yeah. So musig, and what we're doing is we're aggregating the key, and the verifier, confused something there. I'm not sure if I've remembered everything exactly right, but basically the verifier is going to be able to look at it as just one key, verify it as such, and that's very good in terms of saving space, and it's very good in terms of privacy. But it does require that all of us interact in order to create the signature.
And by interact,
look right here, there's something about it that looks wrong.
Is it really the case for non-multisig that we have to interact, at least to send the partially signed stuff around? I mean, unless if we knew the transaction beforehand, I guess.
Yeah. Actually, there's multiple different answers. I mean, yeah, I haven't really thought about that very carefully. I think the other thing that there's more than one way to do it, and it turned out about a month ago that there was a flaw in the security proof of one way of doing it. But it was okay because there's another way of doing it which just changes it from 2 rounds of interaction to 3 rounds of interaction, and that doesn't really make that much difference. Sorry, why do I think there's something wrong here? It doesn't really matter, does it? Nobody's going to check. The paper, I just realised it doesn't really matter, right? Because it's just the formula. The paper, I think it's down here. Yeah, you should check the latest version of the paper because they changed something. But the basic gist of it is that you combine in interaction your keys and you make it safe from this attack, so it's not the case that somebody can do it on their own. And you still have this property that it's private because you've only got one signature and public key on the chain. Other people can't tell even that it's a multi-sig. Not only do they not know who, they don't even know that it's a multi-sig. They only see a Schnorr signature. Yeah. So that's why this kind of thing is so exciting to a lot of the Bitcoin developers. They've been really focused on it for a long time.
Also, where we can put a masked script in that as well, and is it a new construct?
That's Taproot.
Oh, Taproot,
Yeah, Taproot is...
That also uses the linearity.
Yeah, exactly, yeah. So Taproot, I deliberately avoided talking about it here, but this is a very important additional point. So, as well as musig, there's something called Belair-Nevin, which existed before musig, which is another way of doing kind of the same thing, but it doesn't aggregate the keys in the same way because it would require you to publish all of the public keys. And as we know, if you've ever used a multi-sig, have you used a multi-sig before? Well, if you ever do that on Bitcoin, you'll know because you'll see, oh my God, look, all the public keys are published. Hang on a minute, yeah. All the public keys are published, and however many signatures you need are also published. There's a lot of data, right? So Belair-Nevin has a better security or a cleaner security proof, but since it requires all keys for verification, you would have to publish. Because remember, in Bitcoin, verification is not one person, it's everyone. So you have to publish all the keys, oops. And the version, in the latest version of the paper of musig talks about 3 rounds of interaction because you commit to these R values first. Like, everyone doesn't just hand over their R values, they hash them, and they send the hashes to the R values, and that forces you to fix your R value before knowing anyone else's R value, and then you send your R values. And maybe that is or is not necessary, but it helps parents. This is very technical stuff. Yeah, I just said that. So, I mean, I wrote this and I'm not really very sure about it, but there is, again, a link here. It's definitely the case that you can, I think we might know this at least as well as I. But I think if you use MuSig, you can do per input aggregation.
I mean, it's already aggregated.
What's that?
It's already aggregated. There's only one signature you input anyway.
Yeah. In what we've just described, it is. Yeah. But then there's also the possibility of per transaction aggregation. Now, am I remembering this right? That's the one they would use Boolean-Even with. This is very technical stuff. Anyway, there's different ways we can use one or both of these constructions, which are slightly different, but which have this goal of allowing us to aggregate either the keys or even aggregate the signatures, right? So instead of just, we could have multiple signatures aggregated together, just literally added together, but using these clever constructions. And it's all based on the Schnorr signature and combining multiple Schnorr signatures together. There's maybe this, not only this, but there's some talk about this on the mailing lists.
So the per transaction,
very good as well. Yeah.
Per transaction aggregation would mean there's just one transaction in a block.
Oh, but then that's what I put on the third one with a question mark is. What is it?
So I get per inputs, you want to aggregate all the inputs into one input, but then what would transaction aggregation be?
So that would mean one signature per transaction. It's weird because a weird detail that you might not immediately think of is each input, it's not actually the same message that you're signing. Even though you're signing the same transaction, you're signing a slightly different version of it. But you're able, if I understand it correctly, I think it's with this version, to make one signature for the whole transaction, all of the inputs.
With your C hash, where you can change your message.
The messages are all different though anyway.
But I think you just talk about making a C hash where you just make it the same.
Oh, you want to? No idea. Is that possible?
I mean, just like I say, like all you do is sign the same stuff.
Yeah. No. I mean again, I haven't really studied this stuff in depth, so I don't know. But that one's intriguing. I remember you talking about that.
That sounds like it's batch validation.
Oh, and on that side,
add up all the signatures, put in a block, and validate them at once, and it says is either block valid or not.
Oh, that's
so you only do one.
That's another point which I totally forgot to include in all this is that batch validation of Schnorr signatures is possible, but it needs a kind of a trick that's similar to what we talked about, where you have the problem of you get things being subtracted. If you try and verify, so follow the verification equation for lots of different signatures and add them all together, you could do that, but it has a similar security problem. But it actually turns out to easily solved by just adding kind of random terms to each part of the equation. That's another topic which is interesting, but I don't know much about it.
The terms of aggregation would be similar to like Mimble-Wimble, where in the end you just have one mega transaction and a kernel at the end.
Yeah, I guess so, but that requires a one-way. No, sorry, I'm getting lost. There's so many details here, and I don't know most of them, so I don't really want to talk about it too much. I don't think we've got time to do the entirety of CoinSwap, I guess. Do we? Let me just mention what's left here. So we've got a little bit about CoinSwap. We've got something about how you can use a Schnorr signature to make CoinSwap better. Something called an adapter signature.
I don't know what the CoinSwap is.
Yeah. And what was the thing at the end? I can't remember. So, what is a CoinSwap? Anyone else?
It's a way of, you could think of it as like Alice and Bob want to trade coins.
Yeah.
And they do it by way of putting their coins in a escrow and a way of releasing the escrow securely.
Okay.
And it ends up in practice it's used for privacy. That Alice's coins can end up being possessed by Bob and the other way around.
Okay.
So a bit like a mixer that can't run over your coins.
Okay.
So here's
a private atomic swap.
Yes, yeah. So it's like an atomic swap, but with the intention of privacy instead of just trading.
Yeah. So here's a kind of approach that I and several other people worked on, like last year mostly, although it's been talked about for many years. So Greg Maxwell came up with the idea in 2013. But just crudely, this diagram is saying something like, oh, by the way, the sort of blue and the orange is like input-output, okay, just to make it clearer. And for some reason, I'm not going to explain, it's Alice and Carol, not Alice and Bob. I don't know why. Oh, I do know why, but I won't. So basically the idea is that you kind of have, the interesting part is at the bottom here, where you have you heard of HTLC? No.
Yeah.
Hash time locked contract. So the idea is that this output can be spent in one of two ways, right? Either somebody knows a secret value, or somebody else can, exactly, after a timeout, the other person can spend it. So.
Is that inside the script? How do you call it?
Yeah, that's inside Bitcoin script, yeah.
Bitcoin script, so you can... How do you enforce the time? You don't have loops?
No, you do. You have C, or something called CLTV or CSV. So CLTV means check, lock, time, verify. And what it does is you put a value, like a block number in there, and it checks that against the nlock time field, right? And the nlock time field only allows you to broadcast it. It doesn't. The details don't matter. The point is, you put a block height in the script, and the transaction is not valid, or at least that branch of the transaction is not valid until after that block.
You could right now you could lock coins and block 1 million.
So basically, you're not able to insert the transaction and block until that's condition.
It locks the coins until
okay, it makes sense.
some time in the future.
Like, yeah.
So do you know how Lightning works? Because they use the similar concept.
Kind of, like I know the concept behind, but not for sure 100%.
Yeah, this is like a really, really basic compared to Lightning. So it's a similar concept. Is that we can basically what we're doing is we're sort of linking two transaction outputs together and saying we're trying to create a situation where if one gets spent, then the other one gets spent, and if it doesn't get spent at all, then it times out and the money goes back to the start, whoever paid it. And the only thing that's extra in a CoinSwap here is the idea that, well, okay, we set up these weird complicated scripts, but they're not private, okay, because they have a special secret value which links them. So what we do is we create alternative outputs which look like normal outputs. And if both parties agree, then the money goes to the normal outputs. And it's only if one of the parties does not cooperate, then we have to use the non-secret. It's non-secret because it has a secret. No, it's non-secret because it has a pre-image of a hash, you see, which is a very special value that anyone can link. Anyway, the only reason I included CoinSwap in this presentation, and maybe this gives you a flavour, is one example of how the linearity of the Schnorr signature allows us to do clever things. So we're by now familiar with the idea of S equals K plus EX, where E is the hash of the message and the R value and possibly the P value. So what you do here is you embed a secret into the nonce. You have some secret value, which we're calling T, and you add it to K. So effectively the nonce is now K plus T, not K. Right? But apart from that, it's the same as before, because notice we also put T here. So this is the same pattern, we just added an extra variable.
So it's like dividing, yeah.
Yeah, it's just dividing K into two parts, isn't it? Really? We've added an extra variable. And then what we do is we're working with a counterparty. Remember, we want to swap coins privately, let's say. That's the most obvious application. So I'm going to give Chris, not obviously this secret T value, but its corresponding public key, capital T. I'm going to give that to him. And I'm also going to give him something else. This is the clever idea, but this idea comes from Andrew Polstra. So this is the clever idea, is what you do is not just give him that public value, but give him something which is like a signature, but which is not a valid signature. So we call that an adapter signature. Can you tell me why that is not a valid signature? Why is that not a valid signature?
Because it's R plus T.
We know KG is not known.
This is just the S value. Chris said it because there's a T here, right? So the rule of the signature is that this hash is supposed to be the message and the nonce point R and the public key. But here it's not the nonce point R, it doesn't correspond. So if you went through those equations, it would not work out because this K doesn't correspond to the private key of that. Anyway, so you send in the adapter signature. I send in the adapter signature along with T. He can verify, even though it's not a valid signature, he can verify that it is an adapter signature because if he multiplies both sides by G, he gets what he expects to get. So he takes this, which I've given him, multiplied by G, and he asks himself, is it or is it not equal to R plus the hash of the message and R plus T. Now that's why I had to give him T, right? I gave him T before. And part of key and P. Right? So it's like he's doing the verification equation, but he's missing out that there. You know, he's missing out that. But he can check that it verifies. Having verified that, what does it tell him?
You know, okay.
What's that?
You know, okay.
I think so, but that's not what I meant. Okay, I can't guess. I'm forced to guess what I mean. What I mean is, it tells him that if so Alice and Bob. This is going to be Bob. No, this is going to be verified. If the prover gives T, then this is the main idea, which is why I'm labouring it.
Then I can build the correct signature.
Then you can build a real signature, yeah.
So this is the hash. Just it.
Yeah, exactly. Yeah. Think about that, right? So what we're saying is, let's make that clearer because it wasn't very clear. The starting step was I, as prover, create T, set T equal to TG, send to B T, capital T, and S dash, the adapter signature. So what does the verifier do? He checks the adapter signature fits this equation, which is not a proper signature verification equation because there is no plus T here, which there should be to match. But he can still check it, and he knows that if that check passes, that if later the prover gives him the little t, yeah, he can construct the signature himself. Yeah? Because all he's got to do is take S dash and do what? To make a G. Just simply plus T, yeah. Notice he doesn't know the private key. S dash blinds the private key in the same way as an ordinary signature does. But by adding this little t, if he ever gets it, he will be able to create a valid signature using the prover's private key on this message and so on. So this is the basic idea, and like working out the details is, you know, we've been here like more than an hour and a half now. I'm not going to go through this, it's complicated. But basically, the idea is we cooperate to make a multi-sig Schnorr, what am I saying? Key, yeah. You create a Schnorr destination. And the idea is that, this is the really clever part, is that if we make two different adapter signatures with the same T, then if I ever spend my one, I'm going to reveal the little t, and you're going to take the little t, and you're going to apply it to your signature. Think of it as, there's two transactions, one's paying out to me, one's paying out to you. If you take your one, if you're the one who has little t, if you spend your one, you publish the signature, which exposes t, and it allows me to add that t to my signature and broadcast my transaction. So it's functionally exactly the same as this thing here, which we didn't really, this thing here, where we just used the hash function. Well, I didn't say that, sorry. This secret, what it says is, pay to Carol if she knows the pre-image of a hash value. Yeah. It's the same thing though. Here we're using this like a hash function, where this is the pre-image and this is the hash value.
So actually what it does is it does S minus S dash, and then it gets T.
Yeah, that sounds right. Yeah, I believe that's right. S, yeah, so basically it takes, subtracts. Subtracts. Anyway, I don't want to go into detail, but yes, you get it. Again, you can see all of this is coming out of linearity, right? It's the idea that signatures added together or subtracted can do interesting things. And there's another idea called discrete log contracts, which is different from this, but it's a very similar idea where you use the fact that Schnorr signatures are linear, so that when one gets published on the chain, you can either add or subtract it and get some new secret, or maybe claim some coin. So there's many different variants of that idea. Yeah, I'm not going to go through all that because it's complicated. There's just a blog post about it there. Maybe worth mentioning deniability. The cool thing is that when you publish a signature like this, when I actually publish a signature to the chain, claim the coin, now my counterparty is able to, subtract that and get that. But nobody else in the world has any idea. It's just a random number.
Yeah, actually it looks like I spend a P2SH address, which is
yeah.
Well, but it will be a Schnorr 2 of 2 multi-signature. Yeah. But sure, but that's in terms of the redeem script. Yeah. But you can formalize that. But the idea is obvious, right? That it's just a random number. Nobody else knows what's going on. It's a very, very powerful idea, I think. Okay, so I think I'm kind of going to stop because this last step is I'll just mention what it is without going through the maths. But you can try and do something similar to what I just described using ECDSA, but it requires a whole different cryptographic structure called a Palier crypto system, which is completely separate from Bitcoin. It's more similar to RSA actually than to elliptic curves. But anyway, it has some special property which might allow us to do something similar to that, but using ECDSA, which is kind of a lot of fun because then maybe we could do completely private coin swaps even today without Schnorr signatures, which, by the way, I don't really have any idea when Schnorr signatures are coming to Bitcoin. Hopefully soon, but...
Anyone like to make an estimate?
2 weeks.
2 weeks.
Yeah, right, exactly.
I mean, is it sufficiently tested in other applications to go in relatively
When does the patent expire? Is it fully out?
Oh, it expired in 2008.
Okay.
Yeah, expired in 2008.
So we could have started with the Schnorr.
Yeah.
Satoshi didn't know, it was too early.
Has it been sufficiently tested? I mean, obviously EDSA has been.
A lot of the stuff like new signatures was invented specifically for Bitcoin. It was invented at blockstream, so they're building it from the ground up.
Oh, but I wouldn't say from the ground up because that Belair-Nevin scheme is similar. And in fact, if you look at the music paper, it's got a ton of references to people who have tried to do this kind of thing before, and it really hammers home the point that it gives this long list of references, and it says all of these schemes were broken due to variants of that thing where you subtract other people's keys away. But and it's not just a question of being broken; it's also a question is the security proof actually valid? It's maybe we don't have an attack, but if we don't have a proper proof of security, it's kind of scary. Yeah?
When they're using some kind of formal proving for music.
Yes, I mean they've got they have a detailed security proof. I didn't follow it. I barely even tried to read it. It's really complicated. But what happened was about 1 month ago, Gregory Nevin, unsurprisingly one of the Belair-Nevin pair, plus some other people, wrote a paper explaining why the security proof of music with only 2 rounds is insecure. So only 2 rounds means we all make our R values and we all send our R values, and then we use the formula. It's a complicated formula. We use the formula to make our keys and signature, and we all make our signature and we hand out our signatures, and then we can add them together to get the result. But this new paper by Gregory Nevin et al., because I can't remember the other names, said no, that's actually that security proof is not valid, and it's this really long argument, and it was an argument against music and also against there's some kind of threshold signature scheme. Anyway, this is details. Point is, it's not that we know that the 2-round version of the protocol is insecure, it's that we don't have a security proof of it. It's valid.
But the 3-1 is.
But the 3-round is, I think I mentioned this earlier, like the Belair-Nevin one, it's solid. That proof makes sense where you just I mean, this is all a bit beyond me, to be honest. If you read that paper, it's really complicated. And yeah, they had like a whole list of other like people who'd done this stuff before, and some of it doesn't really work. And but my answer to the question, which was like, you know, do we have? Are we sure this is? So I feel like the basic Schnorr signature is more secure, has a much stronger security proof than ECDSA, which is what I was trying to say earlier. But doing this like clever multi-sig stuff, that's another matter. Yeah, it's been like a really well-studied, heavily studied problem, but I don't know.
But it still needs a lot of exposure to the real world. Has it had?
I feel
Has
so,
it had the exposure?
Yeah. I feel like it's a tricky point, isn't it? I'm not really the person to ask, unfortunately. I don't know.
It is simpler, so it must be. It could be.
What's simpler?
The simpler it is, the better. Anyway.
Yeah. We'd think so, wouldn't you? But then again, one of the main points of this was the thing about key subtraction. Right? The simplest possible way to combine signatures is completely insecure, which is interesting, isn't it?
How long it took you to go through all of them and understand them?
Well,
Like, have you read also the papers?
Yeah, I read all the papers. I briefly mentioned it at the start, but what started me on this road, mostly, although I'd studied it a bit before, but what really started me off on this was studying bulletproofs, which is like, it's a much more general idea than this. And it's the idea that you can build these things called, well, that's not true either. It's a zero-knowledge proof system, which was developed in order to create really compact proofs of the range of numbers, which was necessary to build something, oh God, this is terrible, called confidential transactions. How can I boil this down? I was studying something called bulletproofs, which uses a lot of these ideas at the heart of it, and so you'll see left here, like the third item, general zero-knowledge proof systems. Maybe you've heard of ZK Snarks?
No.
No, so ZK Snarks is another one, which is really famous now because I think it's got a lot of traction as ways of not just proving that you know some secret, but proving that you executed a program correctly, honestly.
Mm-hmm.
Yeah. So
It's used in Zcash.
yeah, Zcash is probably the most famous application of it now. So in that case, they're proving something really complicated, like I'm doing a transaction that moves coins from one address to another, but I'm not revealing any other information. I'm proving that the transfer I make satisfies the rules of the system. It doesn't create new coins or whatever. But I'm not. I guess it also proves that I have the right to make that transition, that I know the private key, but it doesn't reveal any other information. So there's no like blockchain analysis because you can't trace the transactions basically, because each transaction is just like a proof that it's valid. That's all it is. So that's much like way bigger kind of achievement than just doing something simple like proving that you know a secret.
And that's the issue with confidential transactions, because how do you prove that they're not spending -2 Bitcoin?
Yeah.
And that's where the whole rent proofs comes in. Then make something that would otherwise be quite simple, way more complex.
Yeah.
Understand all the concepts, you need a PhD in computer science and cryptography.
And I think no one understands deeply all the concepts.
I think you need more than that.
Well, I think you need more than that as well. Yeah, I agree.
PhD is not sufficient.
What about
A few
the
PhDs then.
what about the top one? Has anyone heard of that? Ring signatures, is that? Yeah.
And I heard the name of.
Oh, okay, right. So you know, like Monero. Have you heard of Monero? Right. So Monero uses that concept as like the core of it. Instead of a full zero-knowledge proof system, it just says, "Okay, I'm gonna transfer these coins."
Sure, group of people. Right?
Oh no, backwards. It's like I'm transferring from Alice to Bob, but I'm not going to make it clear that it's from Alice. It could be from Alice or Charlie or Bob. So the signature is valid, but you can't deduce which signer it is out of the whole set.
It's like a multi-sig, but you don't know who signed.
Yeah, you could think like if there was a bunch of generals and they're going to bomb a city, but they don't want their signature on the order, then you do a ring signature so that one of them gave the order, but you don't know which one.
If you make
That's a horrible
chain of
application.
this, if you make a chain of this,
We'll have to cut that out of the
Maybe it
video.
was a funny you had to execute someone. Like they put like bullets.
Yeah.
So no one knows who had the real bullet. But
Yeah, that's
Someone
another
can.
example, yeah.
But I really like that first one because it's so cool. What they do is or at least, no, that's in one type of ring signature. They do this S equals K plus EX. And all they do is they just like, these are different people making signatures. And this E value commits to that K value, not to that one. And then at the end, well, SN, the K value there is committing to that E value. And you get, what you do is you make the commitment as a whole kind of chain, loop.
how do you start the loop?
You can start from anywhere. Because you as a signer only know one of the X's. Sorry, it should be, in this, we know Kn plus E NXN. So you only know one of the X's, so you basically forge all the other S values.
So that also it works out.
It's really cool, I think. That's not the only way to make a ring signature by any means, but it's called the AOS ring signature. Anyway.
DLC is really cool as well.
Yeah. So that was mega long, wasn't it? Sorry. Yeah, sorry it was so long. But hopefully that's interesting.
You can spend one PhD each.
yeah, for signature. Right?
So any general questions? Or specific questions?
I have feedback.
Yes.
I would like to replicate it, so it was very interesting.
That was interesting, wasn't it? Great, thank you. Yeah, I think it's a little bit too ambitious to do so much material, but
Actually,
very interesting topic, right? Yeah.
Actually, not that complex. I did like a toy DLC signature. Interesting. A few lines of code and.
Yeah, I think it is quite a simple. Because
And
can you remind us? His idea is that you make the key be the R and the the R and the P together,
Yeah.
and it determines the S in advance or something, isn't it?
Yeah, you basically so you use the S as a private key, basically.
Yeah, exactly right. So instead of having your public key be P, your public key is P and R together.
Yeah, exactly.
And then how does it work?
So and then it's
you can-
one R per event.
Yeah. So that's what. Yeah. So the P is like fixed, and then you do a whole bunch of them.
Yeah, and only one is fine. I mean, the gist is that the irregular chooses one of the R's, and you cannot choose publish L1 and
So
R2
you
because then you
reveal the private. Again, making use of this
Yeah,
this thing of revealing. Yeah. His.
It's like an oracle that can lie but not double predict.
Yeah. If that's right. That the weakness in the system, isn't it? Is
Yeah,
that you can lie,
But then there's
but
you cannot double lie. I can say black to you and white to this one because then I have to stake some money, of course, because
yeah. So
probably has to have some.
if there's a bond there's like a bond attached to P, then if you make two revelations, you're going to reveal the private key and you lose your money.
And also, the oracle doesn't know who's using the system.
Right. Yeah, that was part of his concept, wasn't it?
Yeah.
I don't find that kind of argument very convincing, personally. Well, I mean, it's this whole thing with game theory. A lot of these game theory constructs are like, somebody could collude, right? I mean,
Yeah, but I can just publish on my website. You don't need to create. I don't need to know who you are. I can just use it. You can also verify. I predict the weather every day in London. You can just say verify all the past signatures is fine. And I don't know that you made that bet of 1,000 Bitcoin in the weather tomorrow. So I could try to cheat, but it's just a random. Unless I know you did it or someone tells it to me.
Yeah, it's definitely very cool.
Or you can do but then what gets really interesting is you can make. I can commit to the price of Bitcoin and USD in 1 year. I mean, in some range because I can't commit to all the values. And then make a transaction that pays you out exactly $1,000.
Yeah.
And then the other party takes the rest of the Bitcoin. So you can make forward.
Did you see there's that guy who published a gist that's actually trying to do was it options contracts or futures contracts using this?
Yeah, it's more like forwards and options.
Was it forwards? Forwards and options? It would be really cool if you could do options with this. That would be amazing.
Because you can't exercise it. You can only exercise the expiry.
Yeah, that's right. Yeah, because you can always do time locks. I don't know. I've got it bookmarked, but I haven't read it
You
yet.
can build a lot of derivative stuff on top of it, which is
If you could build derivatives with that, it would be amazing. Yeah, I'm just worried about the whole kind of
The issue is you need to know-
lie.
no. The thing is with this you can make n of m oracles. It just gets granted.
Yeah, it's
So you can make 3. It's fine. Maybe it doesn't work. And you have to use the exact same format for the predictions.
What happened to Augur anyway? Weren't they supposed to like come out in 2014 with all this stuff?
It was a bit of the crowds. I mean,
The latest is that it's out in July.
Yeah, I think I heard that, but it's just ridiculous how long it's taken. And
But they're relying on Ethereum. So it doesn't,
well, that doesn't help at all. But all the same, I would like to see it actually happen.
there was a lawsuit by one of the guys as well. One of the founders sued the other one.
Yeah, but that's recent news. I mean, it's been like in abeyance for about 2.5 years, isn't it? It's ridiculous. The only reason I mention it is because we come up with all these clever ideas about derivatives and stuff, but nobody's ever actually done it yet. I do really like this because it will be really like off-chain, private, scalable.
Mining to 3 years to come from paper to
That's true.
drawing ticks on a screen, and also like 3 years away from actually people using it in a scale.
It is true, but it was enormously complex. So. But yeah, that's true.
And Bitcoin was like 2009 to 2011. Nothing as well.
That's true. Yeah.
Okay, for the benefit of the video, thank our speaker.
Thank you.
Thank you.
Thanks for having me.